So welcome to Simulation-Based Science, everyone, for the seminar. Today we have a talk from Jaeyoung Kwak, who's from the Complexity Institute in NTU in Singapore. So I worked together with Jay on a project with the Singapore Civil Defence Force, looking at modelling evacuation behaviour as one thing. And we had a kind of a last-minute spot available. So I asked Jay if he would kindly agree to take the spot, and he agreed to stay up. It's now 11 p.m. or midnight to give this talk from Singapore. So yeah, Jay is a postdoc in NTU. He is originally from Korea, but did his PhD in Finland, in Aalto University. And he's been working with us in Singapore for about the last year and a half, where he's focusing on crowd simulation and in particular, trying to model evacuations for the new Singapore General Hospital, which is this massive building with thousands of people involved. So Jay, go ahead, welcome.
Yeah, thank you for inviting me to your seminar. It's my personal to present my studies. So again, I'm Jaeyoung, nice to meet you. And today I'm going to present you some of our research progress in the application and modeling and application of game theoretic models, especially for helping behavior in emergency evacuation. So, okay, so I believe most of you guys somehow familiar with helping behavior. Helping behavior means that I think it's, we can see that people are helping each other, especially when others are in trouble. Especially if we are in a disastrous situation, for instance, a bombing incident or fire and so on, like the situation you can see from the figures. In that case, especially people are willing to help each other. Someone who is in trouble or who can, especially who cannot move themselves to the place of safety. And such helping behavior can be seen from various angles. For instance, in terms of sociology, it can be understood by means of pro-social behavior. In terms of pro-social behavior, people tend to help each other, and by doing that, people try to increase the benefit of others. And it can be also understood by means of altruism, by which people tend to sacrifice themselves to help others, even if it is a costly behavior to themselves. And in terms of evacuation, the total evacuation time, I mean, in which the time, how long it would take to evacuate all the occupants or everyone in the place of danger to the safety. Then if we are helping others who are in trouble, then we can potentially reduce the time that we take to evacuate all the occupants in the place. And in terms of game theoretic models, we can model such helping behavior in terms of voluntary behavior. Based on in terms of voluntary behavior, we can model how such helping behavior can be spread over among the population. And I believe some of you guys are familiar with what game theoretic model is. And I just wonder that if you are not familiar with game theoretic models, I will try to make I will try to make it simple. So don't worry about don't worry that the model I'm presenting isn't that difficult at all. So basic idea of game theoretic model is like we model the strategic interactions among people. So have you ever played rock, scissors, paper game, right? Yeah, okay, so if you are playing the game with, for instance, with your office mate or with your flatmates, then you can think about, you have three choices: rock, scissors, and paper. And then anyway, you play the game once. Then, for instance, you show a rock, and the opponent shows scissors. Then you win the game. But if you play the game for the second time, then you begin to think about how you win the game. For instance, your opponent showed scissors. Then in the case, you might think that some possible ways. For instance, if your opponent is showing, if you guess that your opponent select the same strategy, it means the opponent is showing scissors again. So in the case, you probably think that, oh, in the case, showing rock would be the winning strategy. But if you guess that your opponent is showing something else, for instance, papers, then in the case you think, okay, then scissors would be the winning strategy, and so on. So when you play a rock, scissors, paper game, you are already doing somehow playing a game theory model. And we can extend such idea to many cases, especially when people are doing strategic interactions with others. And in such game series, it is often assumed that individuals or players tend to select a strategy which maximizes the player's payoff. So for instance, if you play your rock, scissors, paper game, you are not trying to lose the game, right? So you always try to win the game, and you try to make your best guess to predict how your opponent, which strategy your opponent is going to show in the next round. And in terms of a game theoretic model, we can model the helping behavior in two types, by two types of players. First type is volunteers, which helps others. And the second type of strategy or players is bystanders. It means that the person or the player doesn't help someone who is in trouble. And we are also going to model altruism, by which we can consider others' payoff. Later I will show how we model the altruism in the modeling of helping behavior in our study. So I believe some of you, if you are familiar with game theory, then you might have seen game payoff matrices like what you can see here. So there are two matrices. So first, I'm going to we can simply think about simple case. So there are two players, volunteer and bystander, and each row, I mean the matrix you are seeing is showing the payoff of row player. And yes, okay, so for instance, if player I is a volunteer, C, and if he or she meets another player, then we can, in that case, the player can meet either volunteer or bystander. If player I meets someone who is also volunteer, then in that case, we assume that both players are getting reward R. But if player I meets bystander, then in that case, player I receives A, which is often denoted as a focus payoff. Means that volunteer is compromising his benefit. For instance, he's spending more time, and he's also taking the risk in case of evacuations. But the other person doesn't cooperate with player I. In that case, player C is taking all the costs by himself. And in other case, for instance, if player I is a bystander, then we can imagine the similar kinds of situation like bystander, player I is a bystander and player J is a volunteer. In that case, just like the previous case, that the volunteer is likely to take all the risk, but bystander is not taking any risk at all. So in that case, we say the bystander's payoff is temptation payoff, denoted by T here. And in the last case, if a bystander meets another bystander, then we assume, then in that case, we say that the payoff is P, which is a punishment. But in case of a fire emergency evacuations, the value of P is often assumed as 0. It means that the bystanders actually don't lose anything at all. So that's the basic payoff matrix. But if we consider altruism effect, by which players can consider other situation. So I'm not sure whether you can see the equation on the right-hand side. So can you see the equation here? Yeah, okay. So in our model, we modeled the altruism by means of making a linear combination of players, the payoff of players I and players J. And altruism is denoted by Q here. And if we control the value of Q, then we can somehow reflect the payoff of player J. So if Q is 0, in that case, according to our equation, then the second term becomes 0. And then we only consider the payoff of player I. And if we increase the value of Q, then we linearly increase the effect of others' payoff. And in our model, we set the value of Q from 0 to up to 0.5. And if the value of Q is above 0.5, it means that the player I considers others' payoff or others' benefit more than his or her payoff. So, and then I would like to briefly explain you about the update strategy or a strategy update rule. So, there are so in our study we consider two players game in which we model the strategy interactions among two people or pairwise interactions. So for instance, if there are two players I and J, and if we assume that player I is a volunteer, then he or she can meet another volunteer. In that case, the payoff difference between players I and J are 0. And if the player I is a bystander, and then if the other player J is also a bystander, then in the case they have a same payoff. In our model, we assume that the strategy update probability is a function of the payoff difference between two players. So if two players have the same strategy, or the payoff difference is 0, it means that the strategy update doesn't happen. But if players I and J have different payoff, then we update the strategy of each strategy of player I. So we define the strategy update probability P delta Uij, like what you can see here, and it is given as a function of the payoff difference between two players and sensitivity parameter K. And the value of sensitivity parameter K ranges from 0 to infinity. And if the value of K is 0, it means that the strategy update probability becomes either 0 or 1, depending on which player's payoff is larger than the other one. And if we set the value of K is infinite, then the strategy update probability becomes 0.5. It means that the update, the strategy update would happen randomly. And in our model, we also considered evolutionary game theory. It means that the strategic interaction among players performed in the course of time. For instance, at time, okay, let's say we are watching the scene of at time t, and we see that player I is a volunteer, but his strategy was updated. We are seeing his current strategy, which is a result from the previous time step, time t minus delta t, like what you can see here. And at each time step, player I is performing a game, is playing the game with other player J. And the player J is in our setup, it is changing. So for instance, at time t, player I is a volunteer and player J is a bystander. And player I is interacting with a bystander, and he computed, or he changed his strategy based on the strategy update probability that we presented the previous slide. Then player I becomes bystander in the next time step. And in that case, the player I changed his strategy, but still he's playing the game. And in the next time step, he meets other players, and then he's and if the strategy of opponent player J is the same as player I's strategy, then the player doesn't perform. In effect, the player I doesn't perform the game, and then continues and then update his strategy in the next time step, and so on. And then now I would like to briefly explain you about the simulation setups. Yes, in our study, we simulated the evacuation of pedestrians in a confined room, which is 10 meter by 10 meter. And there are 100 pedestrians in the room. And there's only one exit, which is on the right side. And the place of safety is right side of the corridor. And all the pedestrians in the room can exit or can egress to the place of safety only through this exit. And in this room, we placed 100 pedestrians randomly, depending on the random sheet values. And then in this room, we placed 10 injured persons, and rest of pedestrians are assumed as passers-by, means that they are not in, and then passers-by means that they can be either a volunteer or bystander. And in our setup, we assume that for each injured person, 2 volunteers are required. So means that if there's one injured pedestrian, then he or she can leave the room with the help from 2 persons. If the injured person has only one volunteer, then the injured person cannot evacuate to the place of safety. And in our simulation model, we assumed that the volunteer is looking for another volunteer who can help the injured person together to evacuate to the place of safety. So by assuming that we can play, we can model the behavior of volunteers based on by means of two players game and then evolutionary game. And in our simulation studies, we also consider the existence of committed volunteers. Committed volunteers are the volunteers who don't change their decision to rescue the injured person. So means that, for instance, if there is one committed volunteer in the waiting room, then that volunteer do not change his or her decision, no matter what, no matter other strategy. And we considered two different cases. The first case is that without committed volunteers. So it means that there is not committed volunteers. So all the passers-by can be either volunteer or a bystander, and they can freely change their strategy in the course of simulation. And in second case, we consider we say with committed volunteers. In that case, we assume minimum number of we can assume a minimum number of volunteers. In our study, we assumed 10 volunteers. So it means that on average, each injured person has one volunteer, and each volunteer has to find his or her peer volunteer who can move the injured person together to the place of safety. And then the movement of occupants in the waiting room is modeled by means of a social force model. According to the social force model, we can model the movement of pedestrians as a summation of internal motivation and response to external stimulus. And internal motivation means that your intention that you want to go, and based on your intention, you can start your destination, and you can speed up, or you can adjust your speed when you move to your destination. And according to external stimuli, you can respond to the existence of other pedestrians or obstacles or boundaries, like columns in the middle of your pathway, or walls and other obstacles in the room. When you are walking around in indoor space, you need to avoid colliding with them while you are walking to your destination point. So the social force model can be written in the equation that you see in the screen. The first term on the right-hand side is internal motivation, and second and third terms are your response to external stimuli, like existence of other pedestrians and the existence of obstacles and walls and so on. And now I would like to show you some result from our study. And yes, okay. So if you see the left side, there are circles which represent pedestrians in the waiting room. And here you can see open circles, that is injured pedestrians. And you can see a full black circle, something like this. And this indicates volunteers who are going to help injured person, for instance, this one or that one here. And you can see full green circles, for instance, this one. This is a bystander who are not going to help the injured person, just who is going to evacuate to the place of safety through the exit here. Yeah, and from our simulations, we could observe the change of strategy or change of decision of players. For instance, we could see the change of we could see that some bystanders turned into volunteer. For instance, if you see a bystander in a red circle here, can you see the red circle, right? Yeah, and after the next simulation time step, this person changed his strategy to become a volunteer. And this person is influenced by nearby pedestrians, especially a volunteer in the blue circle, like what you can see here. And we can also see another bystander, another volunteer who was a bystander previously, but he also changed his strategy to become a volunteer. The other guy is in this red circle, and this bystander was influenced by several volunteers within this large blue circle. And there are 4 volunteers, and one of them influenced on the bystander in the red circle, and the bystander turned into a volunteer after interacting with the volunteer. So after the interactions, we can see that 2 additional volunteers who were bystanders in the previous time step. And we can also see the opposite case in which some volunteers turned into bystander. For instance, if you see the screenshot on the left side, there is a volunteer which is indicated by a red circle here. And he was a volunteer, but each simulation time step, he interacted with other pedestrians within his perception range. Then this volunteer interacted with a bystander, and he turned into a bystander, like what you can see on the right figure. So yes. So in our simulations, we could observe the change of strategies of individual players from bystander to volunteer, from volunteer to bystander. Yes, and then we have been trying to quantify the level of collective helping behavior. So we defined the number of, we counted the number of cooperators, and then we normalized the number of cooperators against the initial number of cooperators. As I mentioned in the previous slides, that we assumed 10 volunteers. I mean, that's the initial value that we assumed, and then we for each simulation one, we see the number of volunteers or cooperators. Once the simulation reached stationary state, then we normalize the difference against the initial value, which is 10. And the value of the normalized fraction of cooperators, or NC, ranges from -1 to 1. And if the value of NC is -1, it means that there are no volunteers in the end. But if we see that the value of NC is 1, it means that we have successfully recruited all the required number of volunteers. So the number of volunteers in the end became 20. And we can look into the change of the number of volunteers or number of cooperators in the course of time. So in the current slide, I'm presenting the case. Okay, this should be without. Okay, without committed volunteers, and we can see 5 different patterns. So the first pattern is that the fraction becomes 1. It means that all the injured persons can evacuate to the place of safety with the help of volunteers. And the second case is that the value of the NC is between 0 and 1. It means that some volunteer and some injured persons can evacuate to the place of safety, but others couldn't find volunteers. So the rest injured persons couldn't evacuate to the place of safety. And the third case is that NC is 0. It means that the number of volunteers is 10 in the stationary state. And it means that there's no additional volunteers joined to the existing volunteers. So in the case, none of injured persons can evacuate to the place of safety. And the fourth case is that the value of NC is between 0 and -1. It means that some of volunteers change their mind to become a bystander. So the number of volunteers in the end is smaller than that number in the beginning of the simulation. And the last case is that NC is -1. It means that all the volunteers in the beginning, they decided to become bystanders. So in the end, there's no volunteer, and all the injured persons left alone without any volunteers. And okay, sorry, this should be with committed volunteers. Okay, and the second setup is that with committed volunteers. In that case, we can see 3 possible outcomes, and the patterns, the 3 cases that we can observe is same as in the case without committed volunteers. The major difference is that the value of NC is always equal or larger than 0. It means that at least there are some additional volunteers we can see in the course of simulation. And somehow this result is not that surprising because in this case we assume that the initial volunteers don't change their decision or their strategy. So in the case, it is natural to see that the minimum number of volunteers is 10, and then we can only see either the number of volunteers is constant in the course of simulation in the course of time, like what you can see on the rightmost panel, or we can see some increment in the number of volunteers, like first and the second panel. And based on our observations, we have characterized collective helping behaviors by means of complete rescue probability. I think, yes, as I mentioned in previous slides, we defined in the beginning of simulations, there are 10 initial volunteers. And if the number of volunteers is 20, then we can see that all the injured persons are rescued. But if the number of volunteers is below 10, it means that if the number of volunteers is below 20, it means that some of injured persons cannot evacuate to the place of safety, because that injured person, those injured persons cannot get the help from volunteers. So there are three possible outcomes, or three possibilities of the value of PR. The first case is the complete rescue probability. PR is 1. It means that all the injured person, in the case, the number of volunteers in the end becomes 20, and all the injured persons can be rescued to the place of safety. And yes, sorry, okay. Then let me explain how we define the complete rescue probability. In our simulation study, we changed the game theoretic model parameters. For instance, the payoff of bystander and the payoff of the volunteer, and when they are interacting together, as I explained before, that there are two types of payoff. One is temptation payoff. The other one is circus payoff. And in our study, we controlled the values of temptation payoff and circus payoff. And then in addition to those parameters, we also controlled the altruism strength. But at this time, I'm presenting the result without controlling the value of altruism strength. So in this case, we only control the values of temptation and circus payoff. And for each parameter combination, we performed 100 replications. And then we count the number of cases in which we observe that 20 volunteers are recruited in the stationary state. And if we see that in every simulation replication, if we see 20 volunteers, then the complete rescue probability is defined as 1. But sometimes, depending on a random sheet and depending on the parameter values, we can see that sometimes the number of volunteers is smaller than 20. Then in the case, the case corresponds to the case that the value of complete rescue probability is between 0 and 1. And the last case is that the complete rescue probability becomes 0. In that case, we cannot see complete rescue in which the number of volunteers is 20. And there are two graphs you can see in the bottom. Sorry, I clicked the wrong button. Okay, the first the graph is showing the case without committed volunteers, and the horizontal axis is indicating the value of circus payoff, and the vertical axis is representing the value of complete rescue probability. And we control the value of temptation from 0 to 2, but in this plot we only show some of them. And if we increase the value of temptation payoff, then we can observe that the complete rescue probability tends to decrease, even if the success payoff is large. So the case without committed volunteers, we can see that if the temptation payoff is smaller than 0.6, the complete rescue probability becomes virtually 0. And then we can see that if the temptation payoff is 0, in the case being a bystander while the opponent is a volunteer is not beneficial strategy at all. So in the case, the suckers or the volunteers payoff, sometimes it can be larger than the other case in which opponent is in opposite case means that so being a volunteer is more beneficial than being a bystander. So this is what the red curve shows such in the case. And if we increase the value of success payoff or being a lonely volunteer, and in the case the complete rescue probability is increasing, but it never reaches to 1, means that without committed volunteers, it is not possible to achieve complete rescue all the time. And then we can move on to the other case in which we assumed committed volunteers in order to make simulations. So in that case, we can see that the complete rescue probability, which is close, it is approaching to 1 if we increase the value of success payoff. Yes, and similarly to the previous the case without committed volunteers, we can see that for higher value of temptation payoff, the complete rescue probability is smaller. I mean, it means that, for instance, if we have if the temptation payoff 0, for instance here, and then if we compare this case to other one, which is 0.8, for instance here, in that case the gap or the difference in complete rescue probability is so large. So means that if the temptation payoff is large, then the chance of achieving complete rescue is less comparing to the small temptation payoff. And then now we are going to consider the effect of altruism. As we discussed in the previous slides, that by means of altruism, we can make player I reflect other players' payoff in terms of linear combination between player I's payoff and player J's payoff. So so in the case, So in the case, we can see the similar kinds of patterns in the complete rescue graphs. So the left columns, the leftmost column shows the case no altruism. The graphs in the leftmost column is what we just discussed. And if we increase the value of altruism, which is denoted by Q here, and we can see somehow qualitatively similar curve, but the value of complete rescue is smaller. It's getting smaller as we increase the value of altruism strength. So especially in case without committed volunteers, we can see that when the altruism strength is 0.2, which is intermediate level, then in most temptation payoff values, the complete rescue probability becomes close to 0 already. And if we increase the altruism strength to higher level, for instance, 0.4, then in the case, the complete rescue probability, PR, becomes 0 in the whole parameter space. And in the similar pattern can be also observed the case with committed volunteers. The pattern is a bit different in the case with committed volunteers. So the leftmost figure is what we observed, what we discussed in the previous slide. And if we increase the altruism strength, then we can see that the minimum values of the complete rescue probability PR is start to increase. So for instance, if you compare the red curves, red scale curves here, this is no altruism strength, and this is intermediate level altruism. And further, we can see also compare it with high altruism strength, which is on the rightmost column. Then the minimum value is it is 0 in the no altruism, and it is around 0.2 in intermediate level. And then it increases a lot if we increase the value of Q or altruism strength too high. And we can see the similar patterns for different values of temptation payoff. But I would like to note that in case of no altruism or low altruism strength, the PR or the complete rescue probability, it can reach 1 depending on the values of temptation payoff and circus payoff. But if we increase the value of altruism strength, especially the case of a high altruism strength, like what you can see on the right side, most right side, that the curves at a glance, they look quite close to the value 1, but actually they are not, but they don't reach to the value of 1. This is seemingly because that still there are more number of bystanders, and if we increase the value of altruism strength, then in the case the bystanders, we tend to consider bystanders payoff, and then we also somehow I mean that if we have a higher altruism strength, then in that case the difference between circus payoff and the temptation payoff is reduced than when the altruism strength is small. So this is seemingly because this is seemingly the reason why the complete rescue probability cannot reach to 1 when the altruism strength is high. And hello? Yeah.
Yeah, and just because I'm looking at the time, it may be a good idea to think about
to wrap up. Okay.
Yeah.
Okay. So
because people may want to ask some questions. That's all.
Okay. Just a few more slides. So I will try to finish them quickly. So, and based on the idea of complete rescue probability, we can draw phase diagrams depending on the value of complete rescue probability. As I mentioned before, that if the complete rescue probability is 1, then we define full cooperation phase, which is FC, denoted here. And if the value of PR, or complete rescue probability, is between 0 and 1, in that case, we can see partial cooperation phase, which is denoted by PC. And if the value of complete rescue probability is 0, then in that case, we define a defection phase. And we can draw phase diagrams in TS space. And depending on the value of T and S, along with Q, we can observe 3 different phases. The left case is without committed volunteers. And the right figure, you see the with committed volunteers. The major difference is that if we introduce committed volunteers, then we can observe partial cooperation in considerably large parameter space. And in some parameter space, we can also observe full cooperation. And yes, but on the other hand, if we consider the case without committed volunteers, in most parameter spaces, parameter combinations, we can see defection phase in which all the injured persons cannot be rescued. And then if we increase the value of altruism strength, which is denoted by Q here, then the phase boundaries in each case without and with committed volunteers are changing. For instance, the case without committed volunteers, the partial cooperation phase is shrinking, like what you can see from here and here. So at some point, when the value of altruism strength is high, then the partial cooperation phase is virtually disappeared. Somehow, similar pattern we can observe the case with committed volunteers, but it happens for the full cooperation phase. And on the other hand, the partial cooperation phase is expanding as we increase the value of altruism strength. Yes, and we can also understand in terms of well-mixed population model. The basic idea is that the time derivative of the number of cooperation is qualitatively different in case without committed volunteers and with committed volunteers. In case with committed volunteers, the time derivative, the value in the red dash, the green box is likely to be negative. So the number of volunteers in the end becomes 0 or smaller than the initial value. But with committed volunteers, the time derivative is likely to be positive. So the number of volunteers is larger than, in the station state, is larger than the initial value, or sometimes it reaches to 20. So yeah, that's about the result of our simulation studies. So I have trying to explain our study of helping behavior model for emergency evacuations. And in our study, we considered without and with committed volunteers. And we could observe different phases depending on the values of temptation payoff and success payoff, as well as depending on the value of altruism strength. And altruism strength is introduced to reflect the tendency that people tend to consider others' payoff. And interestingly, we could observe the change of phase boundaries due to the altruism strength. And in case without committed volunteers, defection phase was expanding as we increase altruism. And the partial cooperation phase is expanding in phase diagram in case with committed volunteers. So that's about my presentation, and the further details are available. You can find further details from our preprint, which is available in archive. So thank you for giving me an opportunity to present our study. And that's the slides that I prepared for today. And now now we can have we can discuss some details, and yeah.
Thanks, thanks, Jay.
Thank you.
So it's a bit late, but we have some time for questions from the audience.
Okay, sorry, I think I took more time than I expected, so sorry about.
It's okay. We started a bit late as well, so if you have a question, just maybe make a noise or type something in the chat.
I have a question.
Go ahead, Vitor.
Yep.
Thanks for the interesting talk. I was just wondering if you. So I was a bit confused with the interaction matrix, but I was thinking that it would be, I think, intuitive to compare these basically levels of cooperation to what one would expect from, you know, a traditional analysis from game theory, where you have these, you know, a prisoner's dilemma versus a snowdrift game where you expect some kind of coexistence, versus a stag hunt where you expect some coordination, and then some harmony game. And as far as I remember, I think, well, for the prisoner's dilemma, you would require like T to be bigger than S.
Mm-hmm.
So, and as long as, if you don't have that, then you kind of expect coordination to show, cooperation to emerge. And so I was thinking, it would be, I think, nice to see, I guess, the effect of the spatial structure that you have, which I think is the most innovative thing here. So have the other one as a baseline, because just with the figures that you showed, it's hard to see kind of the role of the spatial structure that you have. And I wonder if you could disentangle that a little bit more.
Thank you for your question, Victor. So do you mean that, if I understand correctly, at least there are 4 types of games in TS space: harmony, snowdrift, prisoner's dilemma, and stag hunt. I wonder whether you can see the screen.
I can.
Yeah. Okay. So now I'm showing our preprint. I think you can recast your question in terms of the values of TS in TS space. So stag hunt, prisoner's dilemma, harmony, and snowdrift. And okay, I didn't explain in my presentation slides, but so this is the parameter space that we have explored. And okay, maybe I can show you the
So I guess my question is, do you have like a comparison between those values and the ones that you get for the spatial dynamics?
Spatial. You mean spatial dynamics means the formation of volunteers. Is that what you mean?
Yes.
Okay.
Right, you have this spatial structure, right, where people bump into each other, they find what others are doing, and they interact like that. So for instance, as you increase temptation, then from the traditional analysis, you should expect cooperation to collapse. But now, because you have these spatial interactions, that probably affects these dynamics. So I was wondering if you had like a comparison of these.
Good question. Yes.
I guess probably the other one would be a fully well-mixed case where everyone sees everyone all the time, versus one where the radius is very small. I don't know if you've explored the different radius.
Okay, good question. Okay, in our model, we assume that each player is interacting with his or her neighbors within a certain perception range. I think it's 2 or 3 meters. And if it's not like a purely mixed population model, but somehow if but each player is considering others who are within a certain perception range, and then each player is playing or update the strategy, which depends on the payoff difference. So depending on.
Did you vary the perception rate?
Yes, we also changed, but we couldn't see any major differences qualitatively. I think it is mainly because that the room size is small and the number of pedestrians are not that big. We tested only 100 pedestrians, so this is maybe why we couldn't see any major differences depending on the different value. I mean, even if we change the values of perception range.
So Vitor, maybe I can add something. So if you look at the future work in the paper, it's basically this. The question that you've just asked is written down there. Eventually, the idea is if you get a model that can explain something like this, is you can then help design the hospital in such a way that you actually see more volunteering behavior. And the other question is, if you send in a paramedic to a hospital and then people see that paramedic helping people, it's going to have less of an effect than if it's somebody who's a bystander. They see other people helping, they're more likely to also help. So all these questions are basically, like you said, the novelty here really is coupling the crowd simulation, the spatial component with the volunteering game. Yeah.
And I'm sure of course I have to read the paper. You looked into that literature of the bystander effect, right?
Mm-hmm.
Yeah, exactly. So yeah, I think it was before Jay started, we actually spoke with the people in Singapore, and they told us a story about a fire. I think it was in Malaysia, where actually the doctors just ran away and left the patients in a fire. So part of it was about also training the staff, right, and having these people to help. And there's all these people that were looking at the terrorist attack in Paris, where they've been actually asking people why they're helping and how they form these groups.
Thanks.
Yeah, thank you for your additional comments, Mike, and thank you for your question, Vitor.
Anything else? Other questions?
So maybe I've just one question to, well, two things to clarify. So first, so do you find that if you have no committed volunteers and you increase the altruism in the sense that, people are more susceptible to other people's preferences, then you don't get rescue behavior, basically, because everybody's an asshole. You think increased altruism just increases basically, not helping without any volunteers. I mean, that's quite interesting. That's an interesting use of the term altruism. And the second question is, how would you validate such a model? Like, do you create some chaos in the hospital and see, or what's the strategy there?
Okay, Fabian, can you see my screen? But first of all, the slides.
Yeah.
Can you see?
Yeah.
Okay,
No.
So the preprint. Sorry, the preprint I see.
Yeah, you see a preprint? Oh, sorry, I'm not familiar with. Yeah.
I think you have to stop sharing and then share again to show the slides.
Okay.
Yeah, now we see it.
Okay. So yeah, so I think your first question is about the altruism strengths, right? And okay, Fabian, I'm sorry, I didn't fully understand your question. Yeah.
No. I mean, I guess it was more semantics. I mean, I was just wondering whether I understand you correctly, because you looked at the probability of rescue, approaching one, and then basically if you don't have a committed volunteer, even if you increase altruism, all the way to 1 or whatever, you just don't get helping behavior. Is that
yes,
how I interpret it correctly, or?
Yes. Maybe yes. Okay. Then let me just briefly explain you that the payoff. The influence of committed volunteers is very crucial in our study. So means that it's like I'm not sure whether you are familiar with the term critical mass. So the basic idea of critical mass, and also what we found in our study as well is that the initial condition is critical, not only about the initial number, but also the setup as well. So if we don't allow the initial volunteers, if we don't allow them to change your strategy, then they will stay as a volunteer until the end of simulation, and they will act like the snowball, which is attracting other snow, snow in nearby. So small snowball can be an avalanche in the end, and the initial volunteers act like that. But if we allow they change their strategy, in our simulation mode, in our simulation setup, there is this possibility that the initial volunteers giving up to be a volunteer, and they turn into a bystander. I believe there are several possible reasons, but the major reason is that the number of bystander is much more. It's much more than the number of volunteers. That's one thing. And another thing is I think the range of perception. So because of those two factors, I believe that the role of committed volunteers is vital. And and after that, the altruism strength plays effect.
Right. Okay. So I was talking about this one plot that you have where you had the the committed volunteers with and without, and then you increase the altruism, and then basically it just didn't increase the helping behavior when you had no committed volunteers. I was just wondering whether I correctly interpreted that. Okay.
Yes.
Then the second question just about how you would validate.
Good question. And the sad news is that we cannot do near experiment. I mean, especially this time. And and another reason is that I think in many game theoretical studies, it is not that easy to validate and interpret or link between near experiment and the numerical simulations or analytical studies. So I think the validation with near experiments will be my future study. So my answer is that it has been validated yet, and there are some challenges to validate the model that we discussed today.
Right. Okay.
Yeah, thank you for your questions.
Thank you.
Fabian.
Thanks.
Any other questions? I guess most people have to make a move now. Okay, then we say goodbye. Thanks, Jaeyoung, for now it's like gone past midnight at least. It's almost 1 a.m., right? So thanks for...
It's just midnight, 12.
Thanks for staying up, and thanks for giving the talk. Thanks everyone for joining. We'll send an announcement about the talk next week. Is there anything else that I need to announce? I'm looking at the organizers.
I don't think so.
Nope, no more announcements. Okay, so thanks a lot, Jaeyoung, again. We'll see you all next week.
Thank you very much for giving me opportunity and listening and asking me questions. So many interesting questions. Thank you so much.
Bye, Jay.
Bye.
Bye.